So continue on chapter 11, and again, this is back to chapter 11. I apologize, I kind of flipped back and forth. But we're going to be talking now about liquids. Okay, again, we're not going to spend too much time on solids, but liquids are kind of important. So first off, we're going to define something called vapor pressure. Vapor pressure. So please note some definition things here. When you say something's a gas, you're saying that it is in that form at 25 degrees Celsius, which is our standard temperature. If you call something a vapor, that means it's generally a liquid at 25 degrees Celsius. Please understand when I'm describing them, I try to use the term vapor, but understand in my vernacular, sometimes I'm going to say the same thing. So we're talking about a liquid going to a vapor and some properties associated with that. So for your notes, if you would please, we're going to talk about something called condensation and then vaporization. So if you would draw yourself a beaker or a flask, the reason I want you to draw a flask is I want you to put a lid on this flask for you to kind of conceptualize what's vapor pressure means or what I'm talking about. So let's say I have a flask and I put a stopper on it. So it's closed to outside forces. And I have liquid water in there. So that's the wavy lines I'm getting at there. Under any temperature, okay, under any temperature, you will see that some of the water, liquid water particles leave the liquid phase and go to the vapor phase, okay? You know this in your personal life. If you leave out a glass of water over a period of days, you will see that the liquid level keeps getting lower and lower. That's because you're not doing anything to it. Some of those molecules have enough kinetic energy to go to the vapor phase. But at the same time, you have condensation taking place. Okay, so some of the, once it has gone to vapor, some of it comes back down to the liquid. So that's what we call condensation. So I always picture this in a container with a lid, and that is because we have something called its vapor pressure. So the vapor pressure is the pressure exerted by the vapor at equilibrium. So there's going to be a point at which, and I will show you a graph here in a second, that the up arrows and the down arrows are at the same rate. Okay, that's really what equilibrium is focused on, dynamic equilibrium. We will spend some quality time on equilibrium second semester, even more so than we're talking about here. So above this liquid, I have vapor. Okay, so this is vapor above that liquid. Okay, so I picture this with a lid so that I could understand that those vapor particles, gas particles, are bouncing around the inside of this container, the sides of the container, and themselves. So again, when we talked about gases in chapter 10, we talked about pressure is force per unit area. So that lid kind of helps you visualize that. It doesn't need to have a lid, okay? Every liquid has a particular vapor pressure due to their forces. So some liquids, like water, don't like to produce vapor, but other liquids do. So they have a term called volatile and non-volatile, having to do with the forces that keep them in that liquid phase. So high vapor pressure means that the substance is relatively volatile, okay? So sometimes in my brain I kind of get this backwards, but high vapor pressure means something is volatile. And what that means is you have a lot of that substance above that liquid. Okay, so it has what we call weak forces because it doesn't want to stay in the liquid form. It is fine with going to the vapor form. While low vapor pressure, okay, considered to be non-volatile, have what we call strong intermolecular forces. And a great example of that is water. Water has a very low vapor pressure compared to other liquids. It is relatively small, but because it has hydrogen bonding, that's a very strong force. So because you have that force in there, you tend to have most of it stay in liquid form. That's very important for our planet because otherwise all of our surface water would then evaporate and we would not have lakes and streams and stuff like that that we do. Also note that if I have two of the same kinds of substances that have the same forces, the larger the molar mass, the lower the vapor pressure is going to be. So if I have a carbon-based molecule with 3 carbons versus something with 5 carbons, the one with the lower molar mass is going to have the lower vapor pressure, okay, due to the fact that it has less forces. So something like this would have a lower molar mass, less dispersion forces, so therefore you have that relationship. So in your notes, I do have this picture of what I consider to be the idea of a dynamic equilibrium. So the rate of the forward is the same as the rate of the reverse. That's a definition of an equilibrium. But what we're focused on in this particular discussion is the rate of condensation is the same as rate of vaporization. So at the beginning, okay, let's say you have liquid water, okay, and please note that evaporation is taking place at all temperatures, so it doesn't matter what temperature we're at, we will always have some evaporation. So we first need to have something evaporate before we have something condense. So that's why you will see that this is kind of a curve. And once you have equal amounts of condensation and evaporation, you have then reached equilibrium. So it now stays at an equilibrium state. Okay, so that means if I were to sample, okay, this vapor above this liquid after equilibrium has been attained, I will get the same amount. Okay, so once that has been established, that's what the line across means. It's constant and nothing else is taking place. So if I compare, let's say, a beaker of water versus a beaker of ether. Okay, now a beaker of ether has a carbon-oxygen-carbon bond, and I don't expect you to know that, but I do expect you to recognize, if I give you a structure, what exactly is taking place. So if I have a beaker of water compared to a beaker of ether, and I have it closed off, I will see that the ether has a higher vapor pressure. So again, what that means is it has less forces that keep it in the liquid phase. So therefore, more of it goes to the vapor than the water. So you could consider ether to be, in comparison, more volatile than the water is going to be. More volatile than the water is going to be. Now, so thinking of changes from liquid to vapor, we could also discuss something called the boiling point, okay? Now the boiling point is a very specific place. It's not like evaporation where, again, that could take place at any temperature. Boiling point is a specific temperature. So what I've drawn underneath, okay, is essentially a beaker on a hot plate to kind of give you a different perspective of this. So I am drawing little bubbles in there to signify that I'm getting close to boiling, And again, some of these water molecules or whatever liquid molecules, they have enough kinetic energy to go to the vapor phase. But what we haven't talked about is, don't we have an opposite force coming down? So this is what we call atmospheric pressure, okay? So we exist on this planet with a particular atmosphere. And so this atmosphere, our air, composed of oxygen, carbon dioxide, is pushing down on us, okay, depending upon our elevation, so on and so forth. So really, you have two forces here, okay? The liquid wants to leave that phase and go to the vapor, and then you have air pushing down or atmospheric pressure pushing down. So the point at which you have boiling is this, where the vapor pressure is equal to the atmospheric pressure. So that means above this liquid you have enough vapor to kind of exceed the pressure that's being pushed down on it from the air itself. So we have a term for this. We call it a normal boiling point, is at 1 atmospheric pressure, because again, if you are at a different elevation, your atmospheric pressure is going to be different. So we call normal as 1 atmosphere, which is at sea level. So this is sea level. Okay. Do note with boiling points, the higher the boiling point, the more forces it has. So we talked about boiling points early on when we were mentioning things like hydrogen bonding and dispersion forces and things like that. So the stronger the force you have, the higher the boiling point is going to be, because you're going to need more energy essentially to have those liquid molecules escape and have enough kinetic energy to go to that vapor phase. So just a couple other points to make here. First off, thinking of a hot plate, you sometimes can raise the temperature above the boiling point. That's called superheating. So that is why you will see in some cases when we boil water, we put little boiling chips in that, and that's to keep it from getting superheated in one place and then spitting out and causing a safety issue. So you can superheat things above the boiling point before it goes to vapor. And then to kind of, I know it's kind of, I'm going back to solids here. Melting points is where a solid goes to a liquid. So again, as I mentioned back when we were talking about solids, the higher the melting point, the more forces you have. So boiling point and melting point is just going to be interchangeable depending upon if you're a liquid at 25 degrees Celsius or if you're a solid at 25 degrees Celsius. And you can go all the way from solid to gas. That's called sublimation. And I will show you a little schematic of that. And then we have something called heat of vaporization, to kind of give you a definition there. Okay, so heat of vaporization is energy required to vaporize 1 mole of a substance at 1 atmosphere of pressure. And we're going to talk a little bit more about some things we could look at with heat of vaporization. So we're going to come back to a little bit of thermal.